All right, let's pull back the curtain on one of algebra's coolest little secrets. It's a factoring method that honestly feels more like a magic trick than math. It's called the difference of squares, and today you're going to learn exactly how the trick is done. Okay, so think about this for a second. Normally, when you use the FOIL method to multiply two things like this, you get three terms, right? But with x plus 3 times x minus 3, something weird happens. Poof, that middle term just vanishes, leaving you with x squared minus 9. So where did it go? Well, that's the mystery we're about to solve.
See, that disappearing act, it's not random. It's all thanks to a very specific and I'd say pretty magical formula.
And here it is. This is the secret right here. A squared minus b squared equals a plus b times a minus b. That's the key. What this means is anytime you're subtracting one perfect square from another, it's always going to factor into these two neat little pairs with the same terms but opposite signs. This simple formula is basically your blueprint for solving these problems in seconds.
So how do you even spot one of these in the wild? Well, it's actually pretty easy if you just use this 3-point checklist. First, look at it. Are there exactly two terms? Second, and this is a big one, is there a minus sign between them? You need that difference. And third, are both of those terms perfect squares? If you can say yes, yes, and yes, then congratulations, you've found a difference of squares problem.
All right, enough with the theory. The best way to really get this trick is to see it in action. So let's just dive in and walk through a few examples together. Let's start with a classic x squared minus 49. First, let's run our checklist. Two terms? Yep. Minus sign? Check. Are both terms perfect squares? Absolutely. The square root of x squared is just x, and the square root of 49 is 7. So now you just plug them into the pattern. X plus 7 and x minus 7. And that's it. You're done. Okay, let's try one that has a number in front of the variable, what we call a coefficient. We've got 4x squared minus 25. Now, don't let that 4 throw you off. The square root of 4x squared is 2x, right? And the square root of 25 is, of course, 5. So we've got our two pieces, our a and our b. Just apply the formula, and you get 2x plus 5, 2x minus 5. See? The pattern holds up perfectly. All right, here's a pro tip for when things look a little messy at first. If you look at an expression and the numbers don't seem to be perfect squares, don't just give up. Your very first move in any factoring problem should always be to look for a greatest common factor, or a GCF. Pulling that out often reveals a much simpler problem hiding inside. Okay, take a look at this one, 50x squared minus 8. At first glance, 50 and 8, they're not perfect squares, but they do share a greatest common factor of 2. So the first thing you have to do is pull that 2 out front. And what are you left with inside the parentheses? 25x squared minus 4. And look at that, suddenly you have a perfect difference of squares problem sitting right there, which factors to 5x plus 2, 5x minus 2. Just remember to bring that GCF down for your final answer. Every good magic trick has its illusions, things that are designed to fool you if you're not paying attention. Let's go over a couple of the most common traps you need to avoid. This is, without a doubt, the #1 mistake people make. See that plus sign in x squared plus 25? That makes it a sum of squares, not a difference. Remember the checklist? You absolutely need a minus sign. A sum of two squares is what we call prime, which means it can't be factored using real numbers. So whatever you do, don't fall for that one. And here's another common pitfall, the expression x cubed minus 9. It has two terms, it has a minus sign, but is x cubed a perfect square? Nope. For a variable term to be a perfect square, its exponent has to be an even number. So x squared, x to the 4th, x to the 6th, those are all perfect squares. But x cubed isn't. Watch out for those exponents. So we know how the trick works, but why does it even matter? I mean, this isn't just some abstract puzzle for math class. It actually has some very practical real-world applications. Let's just picture an engineer for a moment. She's designing a part and starts with a square sheet of metal. We don't know the exact dimensions yet, so we'll just call the length and width x. The total area of this plate then is pretty simple. It's x squared. Okay, now as part of the design, she needs to cut a smaller square hole right out of the center of that plate. Let's say this smaller square has sides of length y, which would give it an area of y squared. So it's the area of the metal that's actually left over. Well, it's the area of the big square minus the area of the little square she removed. It's x squared minus y squared. Does that sound familiar? Because it should. It's a perfect difference of squares. And this is exactly why it matters. For an engineer, being able to factor that expression into x plus y times x minus y is incredibly useful. This new form can simplify really complex calculations for things like material stress or weight distribution. It basically turns a tricky problem into a much more manageable one. So, you see, the difference of squares isn't just a clever trick. It's a powerful tool, and it's a fundamental pattern in math. It really makes you wonder, doesn't it? What other elegant shortcuts and hidden patterns are just waiting for us, hiding in plain sight in the world of mathematics? If you keep looking, you might be really surprised by what you find.